So as I've worked through the various examples here for the WaveShare OpenEPM1270, I wanted to figure out what it would take to create a project from scratch. You can of course open up an existing project and then modify it. However, I was kind of curious what the steps were and the order of the steps to create a project from scratch. What this project's going to be, I kind of bring this up and show you. There's a little card. Let me grab the photo of it here. So there's this little board that I ordered along with the unit called the 8 push buttons board. It's got a ground pin and it's got a single pin for each one of the switches here. And if I depress a switch like K4, the K4 pin here will be taken to ground. A quick note that this header is 9 pins, whereas the what it plugs into is 10. There's VCC floating out here. When you plug it in, make sure to plug it in the correct orientation with the ground pin all the way to the right on the connector. And basically all this does is each switch will take one of these IOs and ground it. So it's a really simple little board. It's plugged in here, like I said, off to the right. So we know our little board. We're going to go ahead and use the onboard LEDs. Say the 4 onboard LEDs, which are these LEDs here. We're going to go ahead and use these 4 onboard LEDs as our output. I'm going to create various combinational logic on sets of pins on this, and the LEDs will be lit up, basically by the output of that combinational logic. These pins are hardwired onto these IOs on the EPM1270 board. So let me go ahead and close this open project, and we're going to go ahead and create a new project. I'll call this example logic, for lack of a better name. We'll go ahead and create a folder for it. It's going to be built as an empty project. I'm not going to add any files at this time. We'll add them through the IDE. The device on this board is a Max 2, is from that family. And if we take the package, it'll make it easier to find our device. It's a TQFP package that is on the OpenEPM1270 board. If we scroll down here to the bottom, if I can get a hold of that, the second device up is the EPM1270T144C5. So it's the EPM1270 device. It's got 144 pins, and I'm not sure exactly what the C5 designator indicates, but that is the device we have. Like I said, by picking the correct family, which is the Max 2 and the TQFP device package, it makes it easy to get to the device we have. I'm not going to add any additional EDA steps. We'll just take the defaults. Of course, we can review our settings. We'll let this finish building the project. And the core project's been built. In the hierarchy, we have our top hierarchy here. If I look at it from files, I'm actually going to add a file. Gotta remember how to do this. New. We're going to add a new Verilog HDL file since we're working in Verilog. I'm going to immediately go ahead and save this file, even though it's empty, as the example logic.v. This is the top of the hierarchy, and as I understand it, this file needs to match. It's in the folder path we created through the wizard, and we have our file here. I have the source code I want to paste into this file already loaded here. This is what I wrote in a previous project, and let me just copy this all out and go ahead and copy it in here rather than type through it all, and we can talk through it. So although I think this module name needs to match. believe this top, yeah, I'm pretty sure this top module name needs to map to the hierarchy name. And that's how it knows example logic. That's how it knows this is all tied together. So, as I said before, we're going to use the 8 switches on that little 8 push button board. The switches themselves are labeled K0 to K7, and we're going to use the 4 LEDs that are on the board itself. These inputs, the switches are all inputs, the LEDs are output. And I'm, in this case, creating a LED register type for each one of the LEDs. That has to do with how they get assigned in the always blocks. And then in the end, assigned to the actual LEDs. This could be an array. I think it's called a vector of 4, and this could be coded better, but I did this very explicitly like this to make it a bit easier to read. We're going to implement 4 logic functions: XOR, AND, OR, and NAND. And basically we're going to say if switch, so the first thing here, always looking at K0 and K1, if there's any transitions on K0 or K1, 1 to 0 or 0 to 1, we're going to load the LED register with, and this is an XOR function. It could be written simpler, I believe, but it basically says if K0 is high and K1's low, or K0 is low and K1 is high, we have an XOR function. If they're both high or both low, the output here will be a 0. And we implement the AND, and we're going to do it on switches K2 and K3, and it's just, LED register 2 is K2 and K3. 4 and 5 are going to create an OR function. And an AND function is simply an AND function with the output knotted, and we're going to do that on switches 6 and 7. And then down here we simply assign the values from here to the actual LEDs to light them up. So that's pretty simple. This next piece took a bit to understand to get this to work. We need to compile this at this point and make sure there's no compile errors. Compiling this will bring into scope all of the pins we've defined so that I can then go in and actually assign them to pins on the board. So we'll give this a minute here to compile. It takes about a minute. I believe at this point this could actually be ran in simulation. I haven't learned how to do that yet. I'm just going to go straight from code to the board and test on the board. Let this keep compiling. As we can see in here, it's still compiling. And we're through compiling. So we've done the full compile and it was successful. At this point, we now want to assign those pins to device pins and other parameters we're going to need. So we're going to go to Assignments, Assignment Editor. This took a bit of time to figure out here. I was trying to do this in the pin planner in previous examples, and the assignment editor is the proper place to do this. I'm going to double click on the empty 2 here, and I'm going to click on the pair of binoculars there, and I'm going to basically say right now I'm going to ask for all names with no wildcard from the example logic. And what this will get me is this list that has everything we have defined in there. And what I need to do is grab the actual LEDs. Actually, I'm going to step back and I'm going to do this in blocks. For now, I'm going to bring across only the switches. And that'll create this block here of switches, and it knows those are inputs. The next thing we need to do here is search for location. Accept wildcards and groups. We're going to pick location on all of these. There's probably an easier way to do this. And now I need to assign these actual values. And to do that, let me bring back up the little picture I drew. I know that if I remember correctly here, K0 is on IO8. K1 is on IO7, etc. So we're going to start by assigning IO8 through IO1. So for K1, it starts with IO8. So we're going to go ahead and assign pin 8, pin 7, pin 6, pin 5, pin 4, pin 3, pin 2, and device pin 1. So what we've done here is we've taken the K1, well oh boy, these are, you may have noticed what I've done here. Shoot. These aren't mapped correctly. I didn't have these in the actual order 0 to 7 when I first brought this up. So we got to go back and redefine these. K0 is on IO8. So now these all get edited. 8, 7, 6, 5, 4, 3. I know I'm doing a countdown here too. So this is something that's kind of caught me a couple times where I don't have the order here sorted the way I think it should be, and I'm not paying attention to the labels as I edit. Anyhow, we've now taken that K0 to K7 that we defined in the source. We'll go back here and look. These guys right here, and we've defined them as inputs, and we've assigned those. The next thing we need to do here is we need to add, and we'll go ahead and list again, and we're going to grab K0 to K7 one more time. In this case, I need to assign a weak pull-up resistor to each of these. With the switch open, the pin needs to end up being a 1, and we can assign a weak pull-up resistor to each one of these pins inside of the device. And as I just said, what will happen here is if the switch is open and the pin's just floating there, this weak pull-up resistor will pull that pin up to a high. Closing the switch will then connect that pin to ground, and the input will be low. So if I sort this again, we'll see that K0 is a location and it has a weak pull-up resistor that's enabled. Next thing I need to define here now are the LEDs. I'm going to double click down here, or actually double click over here again. I'm going to search. We could do some things like show me only the output pins from the list, and if I list now, I'll only find the LED output pins. They should now show up in the list. I hate the sorting order on this. LED 1, we know from the little schematic I did that LED 1, IO 14, 15, 16, and 17. So IO 14, 15, 16, and 17. I need to tell it this is a location. This is a location. This is a location. This is a location. And 14, 15, 16, and 21. Pin 14. Pin 15. Pin 16. And pin 21. And I'm going to save the project at this point. Some assignments have problems. I wonder why some have problems. That's new. That's interesting. I didn't run into this before. This all looks correct. There's weak pull-ups. Well, hopefully when I compile, I will get messages that they give me some guidance here. Just to kind of recap where we had to compile the first time so that the tool chain behind the scenes became aware of these pins. If you just went straight to the assignment editor, you wouldn't find any pins. Well, let's try a compile and see what it complains about. Of course, this will take about a minute to compile. It's not fast. I remember most of these warnings that have scrolled by here from before. So let's scroll up through the list and see what we got. Number of processors. That just has to do with me consuming all 4 cores on this machine. We don't have a valid subscription. We're on the free version. We don't have a design constraints file. No clock defined in design. I don't believe we need a clock for this example. So the reserve all unused pins has not been specified as output driving ground. So basically all of the pins on the device are going to be, unused pins are going to be grounded. Number of processors again. Another warning, no clocks defined. I'm not sure what that warning was about. I do believe at this point this code will work. I'm going to go ahead and bring up the device programmer. And the start button isn't lit here or enabled here because we haven't actually told it the program and configure. And I've just been checking the verify, just so it does a verify after the programming. It looks to me like the weak pull-ups aren't defined, and I'm not sure why. So that must have been what the warning was. I say that because as I move my hand around the board, I should probably actually stop here and get some video of this, but as I move my hand around the board, the LEDs act weird. And I'll stop at this point and shoot some video so you can see what I'm seeing. So I thought I'd go ahead and show you what's going on here at this point. We've got our little board up here with the 8 switches, and we've got the LEDs down here. And if I get my finger in here and just move my thumb across the switches, I'm not actually pushing them, you'll see the LEDs acting weirdly. And I can actually do this in other places on the board. Just bringing my hand down will light that second LED. And what's happening here is the pull-ups, the weak pull-ups, actually haven't gotten enabled for some reason. And so with the switches open, that input is simply floating. And there's enough capacitive coupling from my hand to pull those low and cause just this random stuff to happen here. Again, my thumb is nearly an inch above the board, and you can see just the effect of my thumb. If I find the pins over here, so it's an odd effect. So what this tells me is those weak pull-ups actually didn't occur. I've obviously defined something wrong. So let's go back and look at the assignment editor again and see if we can figure this out. So Let's jump back into the assignment editor and see if we can figure this out. Oh, I didn't turn them on. That's pretty obvious now that I see it. And actually, it's always interesting to have an issue like this and kind of demonstrate it. So I didn't have the weak pull-up resistors actually turned on here. I'm sure that was the issue. I'm going to go ahead and save this again, and we'll compile again. And I think this will resolve the little issue here. We'll find out. So, you know, the best learning comes from mistakes, and on my channel, I almost always show you the mistakes I make. You know, because I think that's where the best learning comes from, and I'm really happy that we captured that bit of video to show what was going on there on the board. We'll let this finish compiling. And with those weak pull-ups now enabled, I predict this design will work as, you know, this will work as designed. We'll find out here. It's been programmed. I can now see, based on the LEDs, I see that things are working correct. So let me jump back out here and we'll do a little demo of the code. So apologies, I need to reshoot this bit of video as the first piece didn't turn out. This is with the board with the working code actually programmed on. Let's take a quick look at the board. Apologies for the shadow. On the board, I've got the little 8 port buttons, or 8 push buttons, board mounted. They are K0, 1, 2, 3, 4, 5, 6, and 7 of the switches. And this, of course, go from IO8, 7, 6, 5, 4, 3, 2, 1. It's exactly upside down to how I would have wired it, but that's the silk screens versus the board. So on the first 2 switches here, we have a XOR function. On the next 2 switches, we have an AND function. On these 2 here, we have an OR function, and down here we have a NAND function. And those are, of course, driving the LEDs here. So with the first 2 switches being an XOR, if either switch is taken low, you'll see that LED 1 light. There's K0 and K1. And if they both go low, the K0 output is low. Of course, holding them both down at the same time is tricky. There we go. So it's an XOR function. If either input is a 1, the output is a 1. If they're both 0, the output's 0. If they're both 1s, the output's a 0. So that demonstrates our XOR function. The next one is an AND. And the AND function here is implemented on K2 and K3. Right now the switches are both open, so the output is a high. If I take either input low, you'll see that output go low on the second LED there, and if I take them both low, of course it's an AND function, the output stays low. If we move on to K4 and K5, which is here and here, K4 and K5 is an OR function. They're both high, so the output will be a high. With a 0, 1 in, the output's still high with a 1, 0 in. But if they're both low, if I can get them both to go low at the same time, the output goes low, and you see it on LED 3 there. So it's an OR function. Either input's a 1 or both is a 1, the output's a 1. The final key combination is 6 and 7. That is a not AND or a NAND. So right now the switches are both open, so the inputs are both 1s. So the output is a 0 because it's not AND. If either one of these inputs goes low, the output will go high. And if they're both low, the output is high. So we've basically demonstrated a bit of combinational logic. The LEDs down here displaying the output, and the little board here used to define the inputs. So we're back in the code designer, looking at the source code here again, and we'll just recap. We've got that little 8 push button board on the 8 iOS connector. We looked at the mapping for the assignment editor. Those go to pin 7, 6, 5, 4, 3, 2, and 1 on the actual CPLD device. We've added a weak pull-up resistor to each one of these so that if the switch is open on the little board, the input will pull itself up to a 1. And then we've mapped the LED 1 to 4 to the physical pins on the device. And that's the 4 LEDs here. We've defined our inputs, our outputs. We've created a register which essentially holds the value. Inside of the always block, if either one of these changes state, we update the LED register accordingly based on the logic function, in this case an XOR. If either one of these change state, again we load its register based on an and the same for these and these, and then we simply assign the LEDs to the LED registers. Now, a point here, a thing to point out is, recall that on the LEDs, they are tied through current limiting resistors to VCC, which means we need to take the pin on this side low to actually light the LED. So in here, we'll look at the and. I've actually implemented true logic. If either one of these is a, if both of these are a 1, actually, I've actually got, no, I'm looking at this incorrectly. We've implemented the and. If there's a change on either one of these, change the output, and we're saying take those two and them together, the ampersand. So if both of these are high, 1 and 1 gives me a 1 output. So this is for LED 2. However, to light LED 2, we need to take this side of it here to ground. And so what I'm essentially saying is if LED 2 reg is a 1, we know the AND function is outputting a 1, go ahead and invert it right here. And that'll make the actual physical pin a 0, and that'll light the LED up. So I hope these little not symbols make here, they have to do with the fact that the LEDs light up actually on a 0 and not a 1. So these are implementing the true logic functions. There is the AND. And to get the NAND, which is a not AND, we have the AND. And then we invert the output, and that makes it a not AND. So take the AND and invert the output. Hopefully this makes some sense. Hopefully the little demonstration of not having the weak pull-up resistors enabled makes sense. I'll say it for another time here. You have to actually compile the code and get it to compile successfully before you can locate the pins here in the assignment editor. If I actually go in here and search, without that clean compile, when I do a list, I would get none of the pins here. In this case, we're filtering on pins output. If we look at pins input and list, we'll find the 8 input pins. If we look at pins unassigned, we should have no unassigned pins, and we don't. Oops. If we look at pins assigned, we'll of course find all the pins that we've assigned something to. So this is pretty interesting. So we can look at all names. If we had a bidirectional pin, such as we'd have for the little 3-wire serial device, we could filter down to it. And of course, pins all should get us the same thing. Hopefully this made some sense. I know there's 1,000 different tutorials out there on creating simple projects inside of Quartus. I am on day 3, I think, or day 4, probably day 3 of playing in this environment, having never worked in it before. There's a whole lot for me to learn. This is what it is. I hope this was useful. Look forward to any feedback you have on the video when I get it posted, and we'll talk soon.